So here in lecture 12.4, we're going to do a big example. In the previous lecture, we showed you how to build the delay graph, and we defined these very important values: arrival times, required arrival times, and slacks, or as they are called, ats, rats, and slacks. Right? We're going to actually take a fairly detailed example. We're going to walk forward through it and build the ats, walk backwards through it and build the rats. We're going to subtract things appropriately and build the slacks. We're going to look at the worst case, worst delay paths through it. And one of the big things we're going to see is that slack is a hugely important concept. When you know the slacks, when you know the worst case slacks, really you know everything bad and problematic happening in your logic network. So let's go take a look at a detailed example to see how all of this works.
So let's look at a bigger example to see how these ideas work. So what's the first thing we need? Well, we need to know the clock cycle. So let's just say it's 12. And we need a graph. And so I've got a little graph here shown below. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 nodes. Sink at the right, source at the left. Lots of edges with delays on them. And a small lowercase letter under each node so that we can identify and talk about it. So first three nodes on the left, A, B, and C, have a zero edge from the source to them. Going to the right, nodes D and E. A connects to node D with an edge of 1. C connects to node E with an edge of 2. Going further to the right, node F. D connects to F with a 5. B connects to F with a 4. C connects to F with a 1. Further to the right, G and H, two nodes. D connects to G with a 3. F connects to H with a 4. E also connects to H with a 4. Going further to the right, nodes J, K, and N. G connects to J with a 2. F connects to J with a 2. F connects to K with a 3. H connects to K with a 3. H connects to N with a 5. And then J, K, and N all have zero weight edges to the sink on the right. So the primary inputs here are really A, B, and C. The primary outputs here are really J, K, and N. And there's little 3 gray boxes by each one of these, which is where we're going to fill in all the values. So let's just remember that the at is the longest path from the source to the node. The rat is 12, the cycle time, minus the longest path from the node to the sink. And the slack is the rat minus the at. And for now, the problem is small enough, we're just going to look at the mixes, the minimum and the maximum delays by I. We're just going to figure it out and write it down. So here's the same graph: A, B, C, D, E, F, G, H, J, K, N, source on the left, sink on the right. We're going to compute ats, rats, and slacks, but on this slide we're going to compute the ats. And so that's going to be the left box on the little gray box by all of these nodes. And we're just going to compute this. And let's remember this. This is just the longest path, the longest delay, the longest set of adding them together numbers on the red edges from the source. So we can do that by I. So, what is the longest path from the source to itself? And the answer is 0. What's the longest path to the A, B, and C nodes that have zero weight edges from the source? Also 0. What are the longest paths to D and E? Well, there's only one edge to each of them, so it's 1 and 2, the numbers on the edges. What's the longest path to F? Well, now we actually have to calculate something, because you could go through the D node 1 plus 5. Or you can go from the B node with a 4, or you can go from the C node with a 1, and so, you're going to get 5 plus 1 is a 6 for node F. What about nodes G and H? Well, node G, there's only one way to get there, so you go from D with a 3, 1 plus 3 is 4. Node H, it's going to be either 6 plus 4 coming from F, or 2 plus 3 coming from E, so it's going to be the 10. And similarly, we can calculate, the longest way to get to node J is a 7. Okay, the longest way to get to node K is a 12. And for that one, you actually have to go from F, right, with the 6, down to H with the 4, and up with the 2. Right, that's the worst thing that can happen there. And the worst way to get to node N is 10 plus 5 is 15. And then since all of those edges have 0 weight to the sink is just the biggest of those, and so it's 15. And so those are the ats. Longest delays from the source. How about the rats? So the rat will be the middle number on all of these boxes, and the rats are best thought of as starting from the sink and going backwards to the source. And the rats are just 12 minus the longest path from the node to the sink. And so it's sort of the same thing, but just backwards. You've got to follow the edges in the other direction. All right, so what's the rat for the sink? It's the cycle time. What's the rat for all of the nodes, J, K, and N, that have a zero weight connection to the sink? Also 12, the cycle time. What about node G? Well, there's only one edge going out of that. So, the path to the sink is length 2, so 12 minus 2 is 10. Node H, there's actually a couple of ways back. The longest way back to the sink is 5. 12 minus 5 is 7. And so we can just continue this for node F. I'm going to write that. For node F, the rat is going to be 3. For nodes D and E, respectively, -2 and 4. Again, 12 minus the sort of the longest path back. For nodes A, B, and C, respectively, -3, -1, and -2. 12 minus longest path to the sink. And again, the source has just 0 weight. Edge is going to be the worst one of those numbers, -3. So those are all the rats. So what are the slacks? The slacks are easy to calculate. The slacks are just the rat minus the at. And if we can just go look at the at numbers, which are blue, the rat numbers, which are 12, we can just do those easily on every node, and we can calculate everything. And the first thing we'll see is immediately the worst thing that appears, because remember the thing that I said, the worst thing that can happen is you have negative slack. The worst thing that can happen is in this case -3. So we've got the source node has a -3 slack, A has a -3, B has a -1, C has a -2, D has a -3, E has a 2. Node F has a -3, G has a 6, H has a -3, J has a 5, K has a 0, N has a -3, and the sink has a -3 as well. What's interesting is that we can actually trace the worst path from the source to the sink, and the way you can do that is just go look at the negative slacks. Go look at the worst case slack. What are all the nodes that actually have -3? And the answer is the source node, the A node, the D node, the F node, the H node, the N node, and the sink node. Those all have -3s. That is, in fact, the worst path there is. That is the longest path. That's the path that's messed up. That's the path that's 15 units long. Okay? That's the path that gets there 3 units after the capture edge of the clock. Right? That's actually really interesting, because let's think about it. What we did a sort of a forward pass through this graph from the source, and we labeled all the ats. And then we did a backward pass through this graph, and we labeled all the rats. And then we sort of at every single node, we just said, all right, look, what's the rat minus the at? And we got a number. And then what I told you, which was really kind of magical, is, the worst thing that's happening in this graph, go find the worst negative slack number, trace that stuff from the input to the output. That's your worst path. And indeed, that's your worst path. Lots of interesting things going on with the slacks. A negative slack in an output means a missed requirement. That's not a surprise, right? We have we have some -3 slacks going on there. That means something shows up 3 units of time after the capture edge on the clock. A negative slack on an internal node means it feeds a problem primary output. So there's a path from that internal node to some problematic primary output. And the big result is that the negative slack appears along the entire worst case path. Your worst timing violation is at an output primary output with the most negative slack value. And you can always trace a path with this exact slack value back to the primary input, and every node on that path has that exact same worst case slack. This is a hugely useful result, an enormously useful result. So slacks are very important. But beyond just knowing what is the worst case path, slacks tell us the problem gates on the path, right? Remember, positive slack means you have margin. You can make the gate slower, you can make it have less power, maybe have less silicon area, it's a good thing. Negative slacks tell you have a problem, something's got to go faster. And a bigger negative slack tells you something's got to go a lot faster. You're going to have to put some more energy in, make something go faster. So slacks are extremely, extremely useful.